Okay. Good morning, everybody. Since you brought up the exam, I think the exam is planned for the week after we come back from the spring break, which will be the last week of this month.
Wednesday, right? The Wednesday of that week?
We'll see. I mean, that's why we have it the week after, so we can talk about it a week in advance. So when we come back from spring break, we'll decide whether it's on Monday or Wednesday, whether it's a take-home or in class. Okay. So in the previous class, we started the discussion of what we're going to be doing next, which is the second way of the second method of designing our IIR filters is to design a continuous time filter and then transform that filter from the continuous time domain to the discrete time domain. Together, so everybody knows what we're doing. So what we're going to be doing, we're going to be reviewing the Butterworth, the Chebyshev filters, and then after we review them, we'll see how we can take them from the continuous time domain and transform them to the discrete time domain. Okay. So we're going to start with our Butterworth filter. So again, we are on the IIR filter design. The continuous to discrete transformation. And the first filter that we're going to look at is the Butterworth filter. And the nth order low-pass Butterworth filter with cutoff frequency that is omega cutoff has a frequency response that is given by h of j omega equal to 1 over 1 plus omega over omega cutoff to the power of 2n, and this is square root. So this is the frequency response of the Butterworth filter. We can plot the body plots for the frequency response. And the body plot would look something like this. At this frequency, the cutoff frequency, we're going to have a negative 3 dB. And at the zero frequency, it's going to have a 0 dB. And this is the magnitude of h of j omega in dB. And we said this curve goes at 20 multiplied by n dB per decade. Okay. And we did, last time we did some plots of the frequency response. Butterworth. Okay, so this is the frequency response of the filter. And here is the code. Okay. Okay, so let's look at the properties of this Butterworth filter. Now, how do we design a Butterworth filter using a continuous time domain? So let's just show a Butterworth filter. So here is two filters. Here is a first order low pass Butterworth filter. And here is a third order, second order Butterworth low pass filter. Okay. Now what we're going to be doing is we're going to be designing this filter, but rather using a discrete in the discrete time. So let's look at the properties of the Butterworth filter. The first property is the filter is monotonically decreasing. What does that mean? Monotonically decreasing. If I take any frequency and I look at the gain, if I take a frequency greater than that frequency, then the gain at that other frequency is going to be less than, or is going to be less than the gain at the frequency that is smaller. Does that make sense? So the frequency response keeps getting smaller and smaller as the frequency goes up higher. It never goes back. Like there's never a frequency where at that frequency the gain is higher than the frequency that is smaller than that frequency.
No ripples.
There's no ripples. Yes, excellent. So this means if omega 2 is greater than omega 1, then the frequency response at omega 2 at j omega 2 is going to be less than the frequency response at j omega 1. And again, this might look strange, but later on when we look at the Chickasaw filter, it has ripples. So you could have a frequency that is higher, and the gain of that frequency is smaller. Okay, the second property, the filter is maximally flat. And what that means, if I take the 2n minus 1 derivatives of the frequency response hc of j omega at omega equal to 0 and at infinity, then these derivatives are going to equal to a 0. If I take the derivatives at omega equal to 0 and at infinity, these derivatives are equal to a 0. Another property of the Butterworth filter, h at j omega c is going to equal to 1/2. So there's a cutoff frequency that we define as omega cutoff, and the frequency response at that cutoff frequency, the frequency response squared, is equal to 1/2. And therefore, h of j omega c is going to equal to 1 over square root of 2. And this is equal to 0.707, which corresponds to a negative 3 dB. So at the cutoff frequency, the gain is going to equal to negative 3 dB. Another property of the Butterworth filter is that if I take the frequency response squared, I can write it as h of s multiplied by h of negative s. So the frequency response squared, or h of s squared, can be written as h of s multiplied by h of negative s. This represents a causal h of s is causal, and h of negative s is anti-causal. And we'll clarify what that means in a minute. Okay. H of s squared can be written as 1 over 1 plus s over j omega c to the power of 2n, which we can also write it as equal to 1 over 1 plus negative s squared over omega c squared to the power of n. Where is that negative sign coming from? This one?
Referring to J.
Yeah, from the j squared. Okay. Now we can take the poles of this system, of the Butterworth filter, and these poles are located at negative s squared divided by omega c squared equal to negative 1 to the power of 1 over n. Again, this follows directly from here. Negative s squared over omega c squared equal to negative 1 to the power of n, of 1 over n. So these are the poles of hc of s squared. Now we can write this. This is going to equal to e to j 2k plus 1 multiplied by pi divided by n. Where k is equal to 0, 1, all the way to n minus 1. And therefore, we can find the poles of the system and the poles are given by sk equal to omega c multiplied by e to j pi over 2 multiplied by e to j 2k plus 1 multiplied by pi divided by 2n, where k equal to 0, 1, all the way to 2n minus 1. So therefore, if you look at the poles of the Butterworth filter, they are equispaced on a circle of radius omega c. And they are at pi over n degrees apart. So therefore, if I were to plot the poles when n is equal to 3, I'm going to have 3 poles that are going to be at this location, at this and this location, and the angle between them is pi over 3. If I were to plot it when n is equal to 4, I'm going to have a pole here, a pole here, pole here, pole here. And this angle is pi over 4. And this is the S domain, S plane. Together? Make sense? Go ahead. You don't like that we have poles in the right half plane?
Well, no, I'm being pedantic. So pi over 2 is the second pole of the right side, right?
We have 3 poles here, 3 poles here. Pi over 3 is the distance between any 2 poles. Pi over 4 is the distance between any 2 poles. The phase angle between, or the angle between any 2 poles. Does that make sense? So this is also pi over 4. To the origin. This is pi over 4.
I think it was just pi over 2 is vertical, right?
Oh, yes, pi over 2. Pi over 4, we're saying should have been a little bit higher.
Shouldn't there be 2 poles on the...
Pi over 4, I apologize. This is pi over 4. Yeah.
Okay.
Pi over 4 between any 2 poles.
So it's not the origin, it makes sense.
Yes, if n is odd, we have poles on the real axis. If it is even, there are no poles on the real axis. Okay. How can we have poles on the right half plane if this filter is stable?
They cancel each other out.
Okay, that's one option. How can we have these poles here?
Omega C is not equal to 1.
What else? Can we have poles on the right half plane if the system, if the filter is stable? We can't.
So it's not stable?
It is stable. Because we're plotting not HC of S poles, we're plotting HC of S squared. Does that make sense? So
Yeah.
keep that in mind. These are not the poles of HC of S, but rather the poles of HC of S squared. And therefore, if you look here, these poles and these poles represent the poles of the HC of S, the causal part. Does that make sense? Remember, h of s squared, we can write it as h of s multiplied by h of negative s. So these are the poles of h of s, these are the poles of h of negative s. Okay. Okay, we can plot these. We plotted these with the MATLAB. So this is when n is equal to, wrong label. So this is when n is equal to 3. Where is the title that we have there? So here is the poles when it is a third, or when n is equal to 3. And here is when n is equal to 4. Yes, the pi over 4 is the angle between these two to the origin. Okay. Now, since we know that HC of S is causal, its poles are the poles of HC of S squared that are in the left half plane. Okay. So let's look at since it is stable and causal, the roots are in the left half plane. So if we have a second order Butterworth filter, and let's assume omega c is just equal to a 1, then we're going to have poles that are going to be located at pi over 2 apart. So we're going to have a pole here, a pole here, a pole here, a pole here. And this angle between them is equal to pi over 2. Okay, so therefore the poles of HC of S squared are going to be e to j pi over 4, e to j 3 pi over 4, e to j 5 pi over 4, and e to j 7 pi over 4. And the 5 and e to j 3 pi over 4. These are the causal part, the causal roots, the causal part of HC of S. So these are the ones that are in the left half plane. Okay, so therefore, if we know the roots, we can calculate HC of S, which is going to equal to 1 over S minus e to j 5 pi over 4 multiplied by S minus e to j 3 pi over 4, which is going to equal to 1 over S plus 1 over square root of 2 plus j multiplied by 1 over square root of 2 multiplied by s plus 1 over square root of 2 minus j over 1 over square root of 2. And if we simplify this, it's going to equal to 1 over s squared plus square root of 2 multiplied by s plus 1. Does that make sense, everybody? So this is the transfer function, HC of s, of the Butterworth filter that is of second order. Okay.
So it has no zeros?
Has no zeros, yes. Okay. Yeah, the Butterworth filter does not have any zeros. Now we can show that for a second order Butterworth filter, and assuming omega cutoff is equal to 1, the magnitude of h of j omega is equal to 1 over square root of 1 plus w to the power of 2 multiplied by 2. Given that h of s is equal to 1 over s squared plus square root of 2 multiplied by s plus 1.
What's the exponent for the omega in the absolute value hj dot omega?
This one?
Yeah,
2
what's
by
that exponent?
2 multiplied by 2.
2 by 2.
2 multiplied by n, and n in this case is 2. This 2 is n equal to a 2. Okay. So given that h of s is equal to this, I'm going to show that the magnitude of h of j omega is given by square root of 1 over square root of 1 plus omega to the power of 4. So given this h of s, we can calculate h of omega, which is going to equal to 1 over j omega squared plus square root of 2 multiplied by j omega plus 1. And therefore, we can write this as equal to 1 over 1 minus w squared plus j square root of 2 multiplied by omega. Together? H of s, h of omega. How do we calculate what is the magnitude of this? How do we calculate the magnitude? What is the magnitude of this? This is complex. How do we take the magnitude?
Square the real and imaginary.
Exactly. We take the square root of the real squared plus the imaginary squared. So therefore, the magnitude of h of j omega is going to equal to 1 over square root of 1 minus omega squared over all squared plus square root of 2 multiplied by omega over all squared. Again, square root of the imaginary, the square root of the real part squared plus the imaginary part squared. And what is this going to equal to? 1 over square root of 1 minus 2 omega squared plus omega to the 4 plus 2 omega squared. And what is this going to equal to? Square root of 1 plus omega to the 4. Now we could have done this for any order, but this is illustrated for the second order. Does that make sense? For any order is going to equal to square root of 1 plus omega to the power of 2 multiplied by n. Okay. Okay, let's do another example and then we'll move on. Let's show that h of s magnitude squared equal to h of s multiplied by h of negative s, which is equal to 1 over 1 plus s to the power of 2n. For n equal to a 2. This is always true, but we're going to show it for n equal to a 2. So if we have h of s for n equal to 2, h of s is going to equal to 1 over square root plus square root of 2 multiplied by s plus 1. H of negative s is going to equal to 1 over s squared minus square root of 2 multiplied by s plus 1. And therefore, h of s is going to equal to h of s multiplied by h of negative s.
Isn't it the absolute value squared equals that?
Which one? Sorry?
The h of s doesn't equal to h of s times h of negative s equals this magnitude square rooted.
Yeah, magnitude squared. This is going to equal s squared plus square root of 2 multiplied by s plus 1 multiplied by 1 over s squared minus square root of 2s plus 1. And if we multiply these two, the only thing that's going to survive is s to the 4 plus 1. Together? Now, where do we get these polynomials that for the Butterworth filter? So for the second order, this is the polynomial. Where do we get them for other orders? From tables. And therefore, if you look at the class website, I have a link for the for the tables for the Butterworth and the other filters. So this is the Butterworth polynomial for a second order, s squared plus square root of 2 multiplied by s plus 1 for third, for fourth, etc.
Where did they build these tables from?
From what we just did.
From what we just did. I mean, you can get the polynomial from the location of the poles, just like we showed, and then you have the coefficients. Okay. Okay, so this is the Butterworth filter. Now, for our purpose, what we are interested in is being able to design a filter. So let's look at the design steps. Okay. So what is the design specs for designing a Butterworth? What is it we're trying to find when we're designing a Butterworth filter?
Cutoff.
Well, the cutoff is given. I mean, if you're designing a filter, the cutoff is given. What is the only parameter that is not known about the filter?
The order.
The order. Together? So when we look at the filter, the only thing that we do not know about the filter is this n. So the design steps is just to find the order of the filter. So what are we given? We're given the cutoff frequency, the 3 dB passband frequency. We will be given the stop band frequency. And we're given the minimum attenuation in the stop band in dB. Okay. So to determine, are these parameters clear? So we have the frequency response. This is our this is our 3 dB point. Omega cutoff. And we have omega stop, and we want the attenuation at omega stop to be alpha dB. Omega stop. Okay, so we need to determine the filter order from alpha. What is the difference between one Butterworth filter with a certain order and another Butterworth filter with another order?
The attenuation.
The attenuation, the way the filter, this is the difference between them. This goes at 20 dB multiplied by 20 multiplied by n dB per decay. So the higher the order, the steeper that decay is going to be. All of these filters are going to have negative 3 dB at omega cutoff, irrespective of the filter order. The difference between them is that the higher the order, the steeper that decay is going to be. This is higher n. Okay. So given that we want to determine the filter order, we're going to calculate the actual attenuation. And that actual attenuation, we want it to be greater than or equal to alpha. And the actual attenuation of the filter is going to equal to negative 20 log 10 of the h of j omega stop. We want this to be greater than or equal to alpha. And therefore, we know that h of j omega is equal to 1 over 1 plus omega over omega cutoff to the power of 2n, and all this to the power of 1/2. And we know that if I take a log of 1 over a to the power of 1/2, this is going to equal to negative 1/2 multiplied by the log of a. And therefore, we need to have 10 multiplied by log 10 of 1 plus omega stop over omega cutoff to the power of 2n. We need to be greater than or equal to alpha. Is it clear what we've done? We want that negative 20 log of h at omega stop to be greater than alpha.
Yeah.
But here, this is in the denominator, so we're going to get a negative sign. There is 1/2 that is going to cause this to become, instead of at 20, at 10. So this is the same as saying 10 log 10 of 1 plus omega stop to the power of 2n greater than or equal to alpha.
So you just plug in omega stop for omega?
What is it?
Well, you went from like regular omega to omega stop.
Well, this is in general, yes. For this, omega stop, if I plug in omega stop here, it will be omega stop. This is for any omega. Okay. So after we calculate this, we use the tables. So this is going to help me determine the value of n, the minimum order that is going to meet this requirement. And then we're going to use the tables to find the normalized HC or H of S. And then we're going to unnormalize. We're going to replace S with S over omega C. Does that make sense? So the tables has a normalized H of S, which means omega cutoff is equal to a 1. So we have to unnormalize, and then we normalize by replacing S with S over omega C. Okay, let's look at an example and do the calculations for it. So let's say we're going to design, we're going to determine H of S for a low-pass filter to meet the following specifications. And remember, we are designing what kind of filter? An analog filter. Okay, so we are given that we want omega cutoff to be equal to 10 radian per second. We want omega stop to equal to 25 radian per second. And we want the minimum attenuation in the stop band to be 40 dB. So therefore, what do we have to do? We're going to use the formula that we created to calculate the filter order. So we're going to have 10, we want 10 log 1 plus omega stop over omega cutoff, which is 25 over 10 to the power of 2n to be greater than or equal to 40. Therefore, we want 2.5 to the power of 2n to be greater than or equal to 10 to 40 over 10 minus 1. And therefore, we want 2.5 to the power of 2n to be greater than or equal to 9,999. Together? Okay. So we can either solve for this and get the value of n, or we can plug in different values of n. So if n is equal to 1, this is going to equal 6.25. This is less than 9999, so this does not work. N equal to a 2, this is going to be 39. It is less than 9999, does not work. N equal to 3 is going to equal to 244, which is less than 9999, which will not work. N equal to 4 is going to give me 1526, which is less than 9999, does not work. N equal to 5, 9537, less than 9999, does not work. N equal to 6 is going to equal to 59604, which is greater than 9999, which will work. Together? Now we could have done this we could have taken 2n greater than log 10 of 9999 divided by log 10 of 2.5. So I could have taken log of both sides. It's going to be 2n multiplied by log 2.5 greater than log 9999. So this would have given me 10.05. So therefore, what is the n that I can have? If n is 5, it's going to give me a 10, which does not work, because it has to be greater than that. So n is equal to a 6. Okay. So now that we calculated the order of the filter, we can go to our table, and if n is equal to 6, we can take it from here. This is the polynomial for the filter. And therefore, our h of s is going to equal to 1 divided by s to the 6 plus 3.86 s to the 5 plus 7.4 6 s to the 4 plus 9.14 s cubed plus 7.46 s squared plus 3.86 s plus 1. What is this filter? This is n equal to 6 filter that is normalized. What is the last step? Unnormalize it. After unnormalization. And to unnormalize, we replace s with s over omega c. And in this case, omega c is equal to a 10, so we're going to replace it with s over 10. Together? So if you do that, we're going to get h of s that is equal to 10 to the power 6 divided by s to the 6 plus 38.6 s to the 5 plus 746 s to the 4 plus 9141 s cubed plus 74641 s squared plus 38,637 s plus 10 to the power 6. Together? Everybody?
How did you get 10 to the 6 on the top?
Because I'm going to replace this with s over 10 to the power 6. Then I'm going to multiply numerator and denominator by 10 to the 6. Does that make sense? Like skipping a step. Okay. So we can test our filter. We can calculate h at 25, which is going to equal to 0.004096, which is equal to negative 47.75 dB, which is greater than the required attenuation of 40 dB, and therefore our filter is done.
So, whenever you put the specs
Mhm.
positive dB,
This always screws me up. You go up to the top.
so it's greater than 40 dB, it's not negative 40 dB.
No, because this is de-attenuation.
Okay.
We want de-attenuation to be 40 dB. Does that make sense? So if I'm starting at 0, it is a negative 40 dB.
Okay, understood.
Yeah, I understand all this numbering will be slightly confusing, but in your notes, write it so that it is clear. Okay. Okay, so what are the advantages of our Butterworth filter?
You don't need a microprocessor.
Wrong answer. Out. The analog Butterworth filter.
You need one transistor.
You're insisting. Really? You need one transistor? This is what we showed you? This is what we showed you? This is one transistor for a second order filter? Go find this value. Come back. And then we'll see how easy it is to have a discrete one. Okay, so the first advantage of the Butterworth filter, the filter is maximally flat. And what that means, there are no ripples in the pass band or stop band. And the other advantage is it is monotonically decreasing. And a third advantage, it is very simple. The only design spec specification is the cutoff frequency, stop band omega stop, and the alpha, the attenuation in the stop band. Okay. So this takes us to this advantage of the Butterworth filter. What do you think the disadvantage of the Butterworth filter? I mean, so far, it's been very nice, so we didn't see any disadvantage of it, did we?
It's in decibels.
No. Since with the filter, when we look at the frequency response, we always look at the decibels.
I guess the steepness matters on order, so if you need a really steep, you need a super high order.
That's correct, yes. The higher the steepness, the attenuation determines the order. The more attenuation we want, the steeper, the higher the filter order. However, the disadvantage of the Butterworth filter is that it's not efficient. The filter is not efficient.
Power or what?
No, we'll clarify it. For given specs, the filter order N for the Butterworth will be higher than other filters. Together? So something to keep in mind. The Butterworth is a nice looking frequency response, no ripples, no issues with higher frequency having attenuation less than a lower frequency. However, the Butterworth filter is not an efficient filter. And to see why that is the case, if I look at the Butterworth filter, and if I were to compare it with other types of filter, so if I look at the Butterworth filter, the filter looks something like this. Like this, decreases, and it goes down. Have the pass band and our stop band. This is our omega cutoff and omega stop. Now, if I look at other filters that we're going to be seeing, we can look at a filter that might have a frequency response that looks something like this. Together? And maybe I should just modify this a little bit. I'm going to have the same specifications for both of these. So when I look at these two filters, the design specifications that I have is omega cutoff, I want this much attenuation, and omega stop, I want this much attenuation. Make sense? Now what the Butterworth filter is going to do is going to meet these specifications and is going to exceed these specifications at all other frequencies. Make sense? So again, if I were to compare these two filters, this is a Butterworth filter, this is another type of filter. Both of these, I have the specification, which are these two dots that I highlighted here. Both of these meet these specifications. Together? However, for the Butterworth filter, it exceeds the expectations outside of this outside of this point, and it exceeds the expectations here. What does that mean? All what I want at omega stop to have this much attenuation. This meets it, doesn't it? This is how much attenuation. However, the Butterworth not only meets it, every other frequency is going to get more attenuation. The same thing here. I want at the cutoff frequency to have this much attenuation. Every frequency below it, the passband, is going to have this attenuation, which is what I like. However, I did not tell him it has to have less attenuation, this attenuation here. So if I can tolerate something like this and something like this, I'm going to be able to design a filter that has a lower order than that of the Butterworth filter. Understood? Okay. So therefore, just right here, the Butterworth exceed specifications everywhere except at omega cutoff and omega stop. And in the other types of filter, we can introduce or allow ripples to achieve same specs with less order, with lower order. Okay, so this takes us to the second type of filter that we're going to look at, which is the Chebyshev filter. Now there are Chebyshev type 1 and there are Chebyshev type 2. So we're going to start with type 1, Chebyshev type 1 filter. And if we have an nth order Chebyshev filter, that has a cutoff frequency omega cutoff, then the squared magnitude response h of j omega squared is going to be given by 1 over 1 plus epsilon squared Tn squared of omega over omega cutoff, where epsilon is greater than 0 and less than or equal to a 1, and epsilon is called ripple factor. What is this Tn that we introduced? Tn of x is the nth order Chebyshev polynomial. Yeah. So unlike the previous filter, the order is determined by this n, which is the subscript of the polynomial. Together? So h of omega squared is given by 1 plus epsilon squared multiplied by Tn squared of omega over omega cutoff. Go ahead. Question? Question? Okay. Anybody seen the Chebyshev polynomial before?
Yeah.
Where?
Electronic circuits 1.
Excellent. So what is Tn of x given by?
Table.
Eventually, yes. So Tn of x is given by cosine of n, cosine inverse of x. And therefore, if we let theta equal to cosine inverse of x, then Tn of x is going to equal to cosine n multiplied by theta. And therefore, we can generate these polynomials. If I want T0 of x, what is T0 of x going to equal to? 1. N is equal to 0, cosine of 0 is just going to equal to a 1. I can generate T1 of x. What is T1 of x? Cosine theta, which is equal to what?
X.
Which is equal to x. Cosine of theta is equal to x. So therefore, T1 of x is just going to equal to x. Together, everybody? And then we can calculate T2 of x. And T2 of x is going to equal to cosine 2 multiplied by cosine inverse of x. how do we calculate T2 of x? So we're going to do a little trick. What we're going to do is we're going to say, okay, we're going to use recursion to calculate higher order polynomials. And what that means is the following. If I came and said we're going to calculate Tn plus 1 of x, what is this going to equal to? According to our definition, is going to equal to cosine n plus 1 multiplied by theta. Agree? N plus 1 multiplied by theta. But I can use this trigonometric identity. This is going to equal to cosine n multiplied by theta, cosine theta minus sine n multiplied by theta multiplied by sine theta. Agree? Directly. Now at the same time, I can calculate Tn minus 1 of x, which is going to equal to cosine n minus 1 multiplied by theta. What is this going to equal to? Cosine n multiplied by theta, cosine theta, plus sine n theta, sine theta. What do I do next? I'm going to add these together. And if I add these together, I'm going to get Tn plus 1 of x plus Tn minus 1 of x is going to equal to 2 cosine n theta multiplied by cosine theta. But what is cosine n theta equal to? This is going to equal to 2 multiplied by Tn of x multiplied by x. Agree? Everybody? Cosine n, Tn, 2 cosine theta is x. Therefore, we can say that Tn plus 1 of x is equal to 2 multiplied by Tn of x multiplied by x minus Tn minus 1 of x. Is that clear? Now we got this.
Can you go back over how you got 2 Tn of x times x?
Which line?
It's the second line from the bottom. From the bottom.
This one? Tn minus 1?
No, that one.
1?
Yeah, that one.
I added these together. These gonna cancel each other.
Right.
So I just
But how
end
do you go from 2 cosine?
Theta is
n?
equal to the cosine inverse of
Oh,
x.
cosine n theta. By definition, T of n is equal to n cosine of theta. Tn is equal to cosine n theta.
Okay,
Theta equals cosine.
And
I see.
what was the other one?
Cosine theta.
Cosine theta is equal to x.
Because
From here.
Okay. Thanks.
Okay. So therefore, if I go back to my calculations here, I don't need to simplify this. I can just use this expression here, or this recursive formula. If I want to calculate T2 of x, what is this going to equal to? 2 multiplied by x, T1 of x, minus T0 of x. Agree? And therefore, this is going to equal to 2x squared minus 1. I can calculate T3 of x. is going to equal 2x t2 of x minus t1 of x, which is going to equal to 2x multiplied by 2x squared minus 1 minus t1 of x, which was x, which is going to equal to 4x to the cube minus 3x. Okay. Now let's look at what makes these polynomials very special. So all what we've done, we said it's Chebyshev filter. The only thing about it is the polynomial, the Chebyshev polynomial that makes up the filter. Now let's look at these polynomials and see what are their properties that makes them suitable for the filter design. So the first property is that all the zeros of Tn of x are in the range between -1 and 1. All the zeros of these polynomials are going to be when x is between -1 and 1. The second property, Tn of x is equal to Tn of -x if n is even, and Tn of x is equal negative Tn of -x if n is odd. And the third property is that Tn of 1 is equal to 1 for all n. And Tn of -1 is equal to -1 to the power of n. Tn of 0 is equal to -1 to the power of n over 2 when n is even, and 0 when n is odd. And finally, for x between -1 and 1, Tn of x is going to be between -1 and 1. And as x goes to infinity, the magnitude, as the absolute value of x goes to infinity, the magnitude of Tn of fx will also go to infinity. So let's run a MATLAB and see what all this means. Okay. So let me take a snippet of this and put it back in there. So this shows all the Chebyshev polynomials for n equal to from 0 to f4. What do you notice? What do we notice? We should be able to notice all these. First of all the zeros of all these polynomials are in the range from -1 to a 1. So from -1 to a 1, all the crossing with 0 happens in here. After it leaves the 1, there is no more crossing the real axis. If you look here, you should be able to see that when n is even, the function, when n is even, the function is even. When n is odd, the function is odd. So if I look at T4, we see it is even. If I look at this one, T1, it's an odd function. See it, everybody? Okay.
Should they all,
Say again?
did it say that T of n of 1?
Yes, Tn of 1
Oh, right.
is going to equal to 1 for all of n.
And they all do.
And all of these at 1, they're all going to go through this point. At -1, it's going to be either a 1 or a -1, depending on whether n is odd or even. Any questions? Okay, let's stop here.
What's the topology of the Chebyshev? You showed the topology of the Butterworth, but what's the Chebyshev like?
You mean the circuit?
Yes, yeah.
I'll bring a circuit that shows it.
The even one?
But I mean, the circuit itself will not tell you much. It's really the transfer function that makes it a Chebyshev. Does that make sense?
Yeah.
So it might look exactly the same. You look at it, it looks no different than any other circuit. Okay, so one thing I want to mention here, while I'm still recording, this course is only offered in person. Now, I allowed some students to watch the lectures because that might cause them hardship to come to class. So please, when you watch this lecture, send me an email saying, I just watched this lecture. Thank you. And don't tell anybody else. That means only if you are not in class.